what is a growth rate? A growth rate is a way of talking about how quickly a function gets to infinity. So we might say something like x squared grows faster than x, or e to the x is even steeper than x squared. If we say that, we're talking about growth rates. So we can define growth rates by saying that f grows faster than g if you're taking the limit as you're going to infinity and g's on top and f's on bottom, you get 0. So that would mean that f is giving you a bigger number near infinity, giving you 0, meaning this infinity is beating this one. Or you can flip it around. If you put the f on top, this infinity is still winning, and that's how you get an infinity. So what does this mean? Well, this is kind of a natural outgrowth of L'Hopital's rule in a way. A way of comparing functions and what they do eventually. So in this picture, let's look at the picture. We're just looking here even from 0 to 10, but it'll give us an idea of what the growth rates of these functions are as they get really big, as x gets really big. So a natural log of x in comparison is really, really flat. Compared to x squared is up here, and then 2 to the x is even steeper, and x to the x is even steeper than that. So what we would say, according to this picture, it appears that the natural log of x grows slower than x squared, which grows slower than 2 to the x, which grows slower than x to the x. So these kind of double inequalities means growth slower than. So a homework problem might say something like, show which grows faster, or determine the two functions have comparable growth rates. So let's do this for x squared and 2 to the x. So according to the definition, we need to take a limit of one divided by the other. So let's take the limit as x goes to infinity of x squared divided by 2 to the x. Doesn't really matter which one we put on top. Now this limit, x squared as x goes to infinity, infinity squared goes to infinity. 2 to the infinity also goes to infinity. So this is an infinity over infinity form. So we can use L'Hopital's rule. Using L'Hopital's rule, we say that this is equal to the limit as x goes to infinity of 2x over 2 to the x times the natural log of 2. Now the natural log of 2 is just a number, so this again is of the form infinity over infinity. 2 times infinity is infinity, 2 to the x is still infinity times a number gives us infinity. So we're going to use L'Hopital's rule again. So this means that our original limit is now equal to the limit as x goes to infinity of 2 over 2 to the x times natural log of 2 times natural log of 2 again, from another derivative of 2 to the x rule. So this gives us 2 this time on top, and still infinity on the bottom from the 2 to the infinity. So a number divided by infinity, we know that goes to 0. So that means our original limit was actually a 0 limit. So going back to the definition, if the limit equals 0, that means that the one on the bottom grows faster. So we can say that 2 to the x grows faster than x squared. And if we look at the graph, 2 to the x is growing faster than x squared. Now one more thing to say about growth rates is that sometimes functions grow at a comparable speed. So, for example, if you were to compare 3x squared and 5x squared, well then we're looking at the limit as x goes to infinity of 3x squared divided by 5x squared, or 5x squared divided by 3x squared. And we can see that even though that's infinity over infinity, those x squareds are going to cancel out, right? That's going to be the easiest way to do this problem. And this limit is going to become 3/5. Well, 3/5 is an actual number. It's not 0, it's not infinity, it's something in between. And so this means that 3x squared and 5x squared have comparable growth rates. That means they grow pretty much at the same speed. Now you might be asking, why do we care about this? Well, it turns out that growth rates end up having lots of applications in both mathematics and in other fields. Say that we wanted to talk about a population, and we want to say, what is it going to do eventually? Is it going to get really, really big? Is it going to get really, really small? Or maybe it's not even good enough to know, well, this population is just going to keep getting bigger and bigger and bigger. Because maybe you're looking at, the population of frogs and also the population of flies. And the population of frogs is going to be affected by the population of flies if the population of flies isn't growing at as much of a growth rate as the population of frogs, because frogs need flies to eat, right? So we need to be able to compare, we need to be able to say not just that a function is going to keep getting bigger and bigger and bigger, but how quickly it gets bigger compared to other functions. And so then we have a theorem that actually tells us a bunch of growth rates. So it says that if you have a log or any power of a log, that's going to be slower than x to any power, which is slower than multiplying x to the power times the log, which is slower than x to an even higher power, which is slower than any number raised to the x, which is slower than the biggest thing here, x to the x. That grows really, really quickly. And so this just gives us some idea of things we probably really already have known, right? We knew 2 to the x gets bigger faster than x squared. But this kind of gives us a way of formally stating that.